sensibilities also. So the alternative is to not use a linear form, but rather to come up with some sort of functional form that's going to behave better in a statistical sense. It's not going to generate predictions outside the 0-1 range, and it's going to more likely have homoscedastic error terms. And the logit is a pretty good candidate, even though it's complicated to express. It's a function that is S-shaped. It might be like this. It could be a complement, depending on how the relationship between x and y goes. But it never takes on values less than 0. It never takes on values greater than 1. It's, if we call this P the probability of proficiency, then a logistic form isn't 1, 0, but rather it's the natural log of the probability over 1 minus the probability. Probability of 1 minus probability is the odds of something. We'll talk about that in a minute. But it's a fundamentally different functional form. And then the right-hand side of the equation looks exactly the same. We've got task value and then math raw score. Okay, so let's make some sense out of this. Because it's nonlinear, the slope, change in probability as a function of a 1 unit change in x, is constantly changing as you go up this curve. Right? The slope starts out flat, it becomes quite steep, and then it ends up being pretty flat. So in contrast to the OLS linear probability, this is called OLS, is sometimes referred to as linear probability model. Because it's assuming that this probability change associated with a 1 unit change in x is a linear function, right? We put a line. That probability was the same regardless of whether we were high on x or low on x. Now, we're fitting this form. This change in probability associated with a 1 unit change in task value is constantly changing as we go up values of x. So instead of having one number for a probability change, we're going to have to say, well, it's the probability change at some value of x is such and such, and another value of x is a different number, and another value of x is a different number. Yeah.
We need to know this. I mean, how do we calculate the slope there? Like
I'm glad you asked.
I can't remember how to take the derivative of that.
1 over x.
You don't need to remember. And I'll talk about that because you're going to need it to do the problem set this week. But let's become a little more familiar with log odds. P over 1 minus P. So that's log of the odds, because P over 1 minus P are the odds of something. right? So if an event has a 50% probability of occurring, then P equals 0.50, and the odds of P occurring are 0.50 divided by 1 minus 0.50, which is just 1. Even odds. If the probability of something occurring is, let's say 2/3, 0.67, then odds are 0.67 over 0.33, 2 to 1 in favor. Right? This is where the odds language comes from that you know well because all of you go to Las Vegas all the time. Right?
There's winning papers there.
All right, so some people in medical research, people just think about odds ratios. They rarely talk about things in terms of probabilities, but rather they tend to do research on these odds ratios. Yeah.
What's the graph of P over 1 minus P look like? Like, why do we need to take the log of it?
To get the asymptotic properties. So, try it. Okay, so that's odds. And if you think of the equation, log odds, A plus B1, let's say, task value, let's say independent variable, plus this other stuff. Reaching back to your high school algebra, maybe. If you take e to the log of something, it's just that thing. So if you take e, exponentiate both sides, a plus b1 task value. So this e to the log of something is just that thing. So now you're getting log odds is a function of something pretty horrible, right? The exponential of this. But the change in log odds, the change in the odds, change in odds associated with change in task value is just e to the coefficient that you get from the log odds equation. Right? So B1 has this interpretation that a 1 unit change in task value is associated with a B1 change in the log of the odds of something. But if we exponentiate B1, then we get something that's a little bit better, which is an odds ratio associated with change in X. The books are helpful in the readings in laying this out. But the bottom line is just estimate where's this? Estimate the linear form, you get this. If you estimate log odds is a function of the independent variables, you get minus 7.30 plus 0.405 task value. Standard error for constant is 0.42. Standard error for task value is 0.095. And then the coefficient on raw score is 0.134. So math raw score and a very small standard error, 0.006. All right, so this is the straight up logistic regression where log odds is the dependent variable. You end up with this utterly uninterpretable coefficient, right? That a 1 unit change in task value is associated with a 0.405 change in the log odds of being proficient in math. If you have an intuition behind that, let me know. On the other hand, if you exponentiate 0.405, you get 1.50, right? Which says that a 1 unit change in task value is associated with a 50% increase in the odds of being proficient. Of math proficiency. So that's a little bit better because it's a little bit easier to think of odds than log odds. It's still not as good as probability, which is a very nice way of thinking about things. So a lot of people will, instead of reporting, maybe in addition to reporting just the log odds results, which don't have much of an interpretation, they'll exponentiate and produce the odds ratio associated with each independent variable and the standard error associated with the odds ratio. And Stata has two different procedures, logistic and logit. One gives you the log odds results, one gives the odds ratio results. They're exactly the same information transformed a little bit. So it's just how, whether you want your results in terms of log odds changes or odds ratio changes.
So then would a 2 unit increase in task value, would that increase the log odds by double or by 2.25?
A 2 unit increase would increase it by e to the 0.810.
Okay, so you actually have to do it that way.
Yeah, right.
Okay. So you can't just multiply through. Okay.
Right.
And then for a negative association, it's less than 1?
Exactly. Exactly. So if beta 1 is less than 0, then odds ratio is less than 1. Thank you. That's exactly right. So if the odds ratio is 0.8, that's a 20% decrease in the odds. it's 1.2, that's a 20% increase in the hours. So what is e to the 0.810?
Trying to figure that
Oh,
out.
okay.
Oh.
All right, let us know. All right, better but still annoying, right?
No, I don't have anything power except swearing.
What we'd really like to do is take this log odds and somehow convert it into a probability. Right, that would be the easiest. So
2125. Oh.
okay,
So it is the same. You can just multiply through these manually. Like you don't actually have to raise e because I just times 1.5 times 1.5 and it works the same way.
okay.
So each yeah.
So converting annoying logit coefficients into probability changes. Now, we can't come up with some one number that's going to work all along this distribution, right? Because we're fitting this nonlinear function, and the increase in probability associated with 1 unit change in task value is going to be continuously changing as we go along this curve. So what people usually do is convert logit coefficients into probability changes at the mean of all the independent variables. Or at the mean probability in the sample. So let me say what the options are here. Option 1, which is recommended, is to use Stata's marginal effects command. There's a marginal effects option for a lot of nonlinear regression procedures. This gives you coefficients and standard errors in probability form. I'll show you an example of this in a second, but let me just keep going on the list. Option 2, shortcut. Not always as precise as you might want, but it's a change in the probability is just B1, the coefficient that you get from the log odds logistic regression, times plugging in a probability and plugging in 1 minus that probability. So usually pick sample mean for P. So let's say, so the base probability for proficiency is 38.3%. Just remember that. If P equals 0.383, which is the average proficiency in the sample, then this delta P is going to be 0.405, which is the coefficient that we get from the log odds regression, times 0.383, which is the baseline probability, times 0.617, which is just 1 minus 0.383, which gives us 0.096.
I feel like that article did it a way more complicated way, but maybe.
That's option 3.
Okay. Okay.
I'm glad you asked.
I could figure it out and do that's fine.
Well, stick with MFX, right? So option 3, if you actually crank through what a change in log odds means, you end up with the second probability equaling the first probability, P1. You want to start out at a baseline probability, you want to know where you go from there, right, with the 1 unit change in cast value.
Yeah.
So it's probability 1 times e to the coefficient times whatever unit change you want in cast value, divided by 1 minus P1 plus P1 times e to the coefficient times the change. Aren't you sorry you asked?
That's fine.
So if it's a 1 unit change, then these delta x's just equal 1. That helps a little bit. But if you want to plug in what new probability you get from some baseline probability, so again, it's going to depend upon where you are in this curve. Pick, 0.383, let's say. That's the overall fraction of the sample that's math proficient. That's P1. E to the beta 1, we saw it was 1.50, right? And then it's 1 minus P1, 0.617, plus that same thing. So that will give you the proper second probability. This is an approximation to that. So if we look across all these different methods, coefficient, standard error, and T or Z ratio are essentially the same thing. OLS we saw was 0.066, standard error 0.015, and if you divide the two, it's 4.52. The log odds, original logistic form, we have a 0.405, standard error 0.094. The ratio is 4.27 as opposed to 4.52. Odds ratio, exponentiating this 0.405 gives us 1.50. Standard error is 1.42. The Z ratio is 1.27. So it's not, with odds ratios, it's not just odds ratio divided by standard error. There's a separate way of calculating significance. If you do marginal effects from log odds, right, so it's just running the logistic regression and specifying that you want the results expressed as marginal effects. And that's giving you 0.089, standard error 0.021. And 4.27. There's a pattern here. If you do beta times probability times 1 minus probability, it's kind of shortcut, or I should say B1 here. You get 0.096. And if you do option 3, I won't repeat the formula, you get 0.098. All right, so the ones that are directly comparable, because they're all attempts to estimate a probability change, are the OLS, the marginal effects of the log odds. Right, that was converting the logistic regression into a probability change. This was attempting to do a shortcut method for probability change based on the logistic regression coefficient, as was option 3. So you're getting similar numbers here. OLS looks like it's understating. In terms of statistical significance, things are very, very similar. You get the same kind of conclusion that it's highly significant. So most journals won't accept just OLS. They'll want to see logistic regression, but you can still present the results either as odds ratios, which is often in the medical literature, but I think it's much clearer to present the coefficients of standard errors as in marginal effects forms, because then all the coefficients are all about probability changes evaluated at the mean. Yeah.
So marginal effect is just the slope of one point on the line?
Exactly.
But
and well, you can plug in whatever point on the line you want, but the default is just to take the mean values of all the independent variables, which is like the mean for the sample.
But I mean, if the curve changes slope all along it, what's the use of knowing the slope at one point?
It's telling you the slope at that one point. It's telling you the slope at the concentration, midpoint concentration of the sample.
So that's why they do it by the sample rather than just the 50%.
Right.
Okay.
And it's just a lot clearer to think about than 0.405, and I find it easier to think about than odds ratios. But that's your own preference.
So we would say at the midpoint of the sample, a 1 point increase increases the chance of you graduating by 0.09%, or 9%.
8.9%, yeah.
Yeah, 8.9%.
Percentage points, right?
Okay.
Right. All right. So, see, I didn't think I was getting to all this stuff by the end of the lecture, but
I had my doubts. The session tomorrow.
we made it.
The session tomorrow, that's just review, right? Not new stuff.
Yeah, right. So I'm not going to come with anything to talk about other than what you want to talk about. Yeah, so we've covered a lot now, right? And whatever questions you've got so far, we can talk about. See you tomorrow. Well,
Yeah.
Ted, you didn't get a room for tomorrow, did you?
No. You want me to get
Yeah, if you could.
this one or?
This one's fine. What time is it tomorrow?
I'm planning to get there.
11:30.
11:30?
Did the equation come thing with the
Thanks.
word, the new one?
No, older one. All of them.
Never used it.
Yeah.
I think we're all getting it.
I feel bad.
I didn't insert the equation.
Share what I was writing, but then I was like, I don't want people to feel like they need to
Figure out, this is
give me that would have been like,
How do you do?
but it's a real time.
But it helps sometimes to be in that midway and then come thing and
Yeah.
I think actually
What that means is